Hey, all right, so we're gonna do some program stuff. I'll teach you how to use these different programs just to do some simple calculations of frequency and period, and also loading in sounds. Okay, so first, I'm gonna have you look at Audacity. We're just gonna go in alphabetical order. It seems to make a little bit more sense. So here's Audacity. The link is going to be, you'll find the link in the, where this video is in the module details. If you want to use Audacity, which you'll know after you watch this video, you'll click on download Audacity, and then you can download the right one for your system. So I've got Windows, so I'd click here. I've already downloaded them all, so I won't go through all that, through that whole process. But this is where you'd go. If for some reason you need an older edition, you can get older editions. Let's see, where do you get older editions? I think over here, Legacy Windows. That's where you'd find your older editions in Legacy Mac. There really shouldn't be a reason. This one, there's not a lot of issues with older computers using these programs, so you should be fine with almost all of you with either just regular Windows or regular Mac. Okay, next we'll look at Praat. Here's these cool dudes that made it. And again, you've got up here for your different machine. So you've got Windows and you've got Mac. Again, I've got Windows, so I would click here, and then I would choose, and here's where you might have to make a choice depending on your computer. You either want to do the 64-bit or the 32. If you have a newer computer, you've probably got a computer that needs the 64-bit version. If you have an older computer, it kind of depends on how old it is, but you might need the 32-bit version. If you don't know if you have a 64-bit or 32-bit edition of Windows, you can find that out if you go to like your computer details. If you don't know how to do that, send me an email and I'll show you. Another option is just if you download one and it doesn't work, download the other one. Okay, and then lastly, WaveSurfer. They've got everything loaded up here on SourceForge, so this one, you shouldn't need older versions, although that's not quite as true for Audacity. I mean, 90% of you'll be fine by just clicking this download link, and you'll be fine. I think that's for Windows, though. If you need the Mac version, you can find that right here. If you need any other additions, click on Files, and then open this little WaveSurfer file, and in here you can find all, well, when there's not so many ads everywhere, you can find all of the older editions. So if for some reason P6 doesn't work, jump back to like P3 or something like that. And then within this 1.8.8 P3, you'll find Windows and Mac and other things that if you're using Linux, I think you probably know that you're using Linux and you know more about your operating system than I do, so I can let you take it from there. But for the rest of us, it's either going to be Windows or Mac, this OSX link right here. Okay, so that is downloading the programs. Let us get out of that. So, Audacity, this is what Audacity looks like. I've got 3 different files that you're going to be working with. Those are in the module as well. You've got 500 Hertz, you've got 500 complex, and you've got E. And I'm going to show you how to load those in. So first, we're going to look at Audacity. If you, I'll put time codes in for when these things actually start. So if you have watched this and you decide that you want to use Praat or WaveSurfer, I'll have it so you can just go further in the video to those areas. That's not going to be in the module description. That's going to be in the YouTube area, so you can just click on the actual link to get to that time zone. or to that time code, rather, not time zone. All right, so you're going to go to File, Open. This is not the right place. So you get to watch me navigate through through everything. There we go. All right, so we're going to start with 500 hertz, and we're going to open that file. Why can't you see what's happening? Oh, because it opened over here. Sorry, it opened on my other screen. Okay, so here's 500 hertz. It's 1 second of 500 hertz tones, the same one that I generated earlier for us to look at. If you zoom in, you can see that this is a sine wave. Great. If you play this back, which you can do by either pressing the space bar or pushing this play button here. So space. Cool. Here, let me turn my... Yeah, very, very nice pure tone. Okay. So you can calculate this if you zoom in. There we go. All right, that might be too far. Now we're starting to see the inside of the matrix here. Actually, this will work. So you can go from this cycle to this cycle right here, and our distance is from 0.002 to 0.004, which means we've got a distance of 0.002 seconds. And I'll bring up my... So you've got from 002 to 004, which is 0.002 seconds. And just double check my handy calculator here. 1 divided by 0.002 is 500 hertz. Great. Hooray. So now we know that it's right. I told it to generate 500 hertz. It did generate 500 hertz. That's great. So my machine keeps, the video keeps starting and stopping. My recording of it keeps starting and stopping. So I don't remember if this cut out before I played the sound for you. If it did, then I'm going to play the sound for you right now. If it didn't, then here's a sine wave again. All right, so a nice little sine wave. That's a pure tone that you heard there. All right, so that was calculating our period, or calculating our frequency from period. Now, one thing that I want to show you is a spectrogram. No, let's do the spectrogram second. First, what I'm going to show you is we're looking at time domain right now. So we've got time here and amplitude here. So amplitude's on the y-axis, time is on the x-axis, and this is just our typical, time domain graph. So let's select a portion of it, and we're going to go to Analyze up here, and then Plot Spectrum. And now we have a frequency domain graph. You can see that we've still got amplitude here. Amplitude in this case is not done from 0 to 1. It's done in decibels, but it's essentially the same thing. It's still amplitude. And here on the x-axis, now we've got frequency. So you've got two things down here. You've got one that's called cursor, and that's just showing where your cursor is. And so it changes depending on where you are. So you can be, you can try to measure with cursor, but you're going to be imprecise. This one called peak right here is measuring where the peak of this graph is. And it's going to snap there
to the closest one for you. So you get your cursor close and peak will snap right to where it should be. So you can see here that the peak amplitude, the frequency of the peak amplitude is 498. We know that it's 500 because I generated a 500 hertz tone, and we also calculated it ourselves that it was a 500 hertz tone. 498 is pretty close. The reason that it's not totally accurate is the size of the window that we're choosing. So the actual how close this is, 498 here, will change depending on our window size. So here we get 501. It's a really good, strong peak at 501 hertz. If we go even, there's not enough data for that, and also I could select more, and we could do that. So we can get more precise the more data we have. But the problem with that is when you're dealing with speech sounds, you don't have a full 1 second of the sine wave. So here, what if we did grab the entire full second that I have here? Go to Analyze, Plot Spectrum. Now we can change the size of our window. Aha! And the peak snaps to perfectly 500 hertz, which is cool. We get a great, look at how perfect this graph is. It's, the thinner that this little purple line gets, that means it's a more precise measurement. You can see that where we were before at 1024, there's some slop around here, right? It's showing that there's a little bit of energy everywhere between 0 hertz and 500 hertz, a little bit. And then there's a little bit of energy up to about 2000 hertz. We know that's not true. The reason why it shows up that way is just the algorithm that the computer's using. And so the more data you can give it, the more sure the computer is about what's actually happening, about where that information actually is, about what the frequency actually is. But of course, like I said, and even 1 second of a sustained sound isn't enough data for this large of a window. With speech sounds, we're not going to have 1 second of sustained a sustained vowel, right? So let's say we go like eat more vegetables. We didn't have a full second of that E. We just had eat. So, a half a second, maybe less. Eat more. O is a little extended, but it's still not 1 second. So we can't rely on these really good measurements. We have to do enough to be able to tell what the, say, the fundamental frequency of someone's voice is, or where the formants are. Anyway, we'll talk about that more in depth in the future of this class, but essentially, you can set your window size to 1024, and you're still going to get really close to 500 hertz here. Okay, now the last thing I want to show you before we look at the next speech sound is a spectrogram. So how I got there was up here, the name of the file. There's a little drop-down menu. Click on that, and then you can change your view. You can change it to a spectrogram. Now, your axes have changed as well. This is still time. The x-axis is still time. You can see that up here. But now the y-axis is not amplitude anymore. The y-axis is frequency, which is cool. And then there is a third axis here, and that is amplitude. The third axis is done in brightness of color. So you can see that there's gray for nothing, and then it goes to blue for a little bit of energy, and then it's this like white hot color for extreme amounts of energy. So you can see that the energy is centered around right here. This would be 0.5 K, which stands for 0.5 kilohertz. Hertz is just like a gram or a meter, where you can tack kilo onto it when it gets to be 1,000, right? So it's 500 hertz or it's 1,000 hertz, and then you can say 1 kilohertz for 1,000 hertz. So then 500 hertz would be 0.5 kilohertz. Anyway, you see here 0.5 kilohertz is where all of this energy is focused around. All right, so that's a spectrogram. Usually we're used to only seeing 2 axes, right? We're used to seeing either amplitude and time or amplitude and frequency, and we can derive one of the others from that. But in this graph, we actually get all 3. Okay, let's look at a different file. Now we're going to look at 500 complex, and I want to say, what do you think? So here's what the file looks like up close. And I want to ask you, if we look at this wave, you can see that it repeats again right here. So we go from here to here. And I want to know, what do you think the fundamental frequency is going to be? It goes from about 0.008 to 0.01. So 0.01 minus 0.008 is 0.002. And holy crap, we just looked in the last file that 0.002 corresponds to a 500 hertz tone. But this doesn't look like a sine wave. This doesn't look like our 500 hertz sine wave because it's a complex tone. But we can still see from where this repeats again what the fundamental frequency is. All right, so let me show you a little secret also. Down here, this says start and length of selection. So you could use your markers up here, like we've been doing in all of the modules up until now. But you could also look right here, and this is giving you the length. So this is giving you the start of your selection, 0.008, and how long it is, 0.002. So, I mean, I could select that much, and it's telling me, well, there's not enough significant figures on here, but we can extend it a little bit. There, 0.001, 0.004, 0.008. So you can measure it that way too. Audacity will give you the measurement, and you don't have to compute it yourself. So that's a little bit of a cheat, but also makes things a little bit easier for you. Okay, so let's take a look at, let me zoom out. Let's select the entire file. Let's go to Analyze, Plot Spectrum. There we go. Now we've got 3 perfect peaks. And this corresponds to exactly what I told it to have. So I wanted it to have a 500 hertz tone, a 1,000 hertz tone, and a 1,500 hertz tone. And what comes up with this window size is 498, 1003, and 1502. Very close. Close enough. We can get better. So if you do this, 500, 1000, 1500. So it's perfect. We made a huge window size, and it knows exactly what we put in there. But again, with speech sounds, we're not going to have a full second of a sustained tone. So it's a little unrealistic to expect that. Okay, so let's go back to 1024. I want to show you also, you can turn grids on, and then you can kind of see like where the frequencies are. Briefly, I want to mention Audacity measures things logarithmically. So that's why the spacing between 500 and 1,000 looks different than the spacing between 1,000 and 1,500. It's not. It's 500 hertz each time, but this is a logarithmic scale. Now, you don't have to keep it at log. Down here in axis, you can turn it into a linear frequency. And then you can see that these are a little, let me turn off grids. There. You can see that these are a little more evenly spaced now. 500, 1,000, and 1,500. The reason why we use log frequency is because if you think about the way that harmonics work, right, they're going to be multiples of one another. So let's say you have let's say you have a 500 hertz tone. So you have 500 hertz, 1,000, 1,500, 2,000, 2,500, 3,000. And if you're doing that, and you're looking at this entire band of frequency right here, up to, even over 20,000 hertz, it's going to be hard for us to look at individual peaks between these 500 hertz areas. I mean, this is 500 hertz right here. There could be a lot of things going on in between that, and we wouldn't see it so well. So we can switch to log frequency and get a better resolution on what's going on in those lower frequencies. The lower frequencies are usually where speech sounds tend to be. Our fundamental frequencies, it depends on gender, it depends on age, it depends on from person to person as well. But they're not going to be over 300 hertz usually. So if we're talking about things in this region, and then they're going to be doubling at 600 and then at 1200, a log frequency allows us to see a little bit more what's going on. But we can make it a linear frequency. Okay, so I'm going to turn that back to log. And I'm going to get out of that. Okay, so now I want to show you the spectrogram. Doink. And let's make this a little bit bigger. And now you can see that there's 3 bands of energy. That changed color just because it was highlighted, and then I deselected it. Alright, so now you can see there's 3 bands of energy, one at 0.5 kilohertz, one at 1 kilohertz, and one at 1.5 kilohertz. Great. That's totally cool. Oh, there's one last thing that I want to show you, which is, this is what a 500, 1,000, and 1,500 hertz tone sounds like.
Kind of more like an organ. Here, let me do it again. Yeah, more like an organ.
In fact, if you are a fan of older music, there's a
song called Lighter Shade of Pale, and this sounds exactly like the organ that's used in that song. In fact, this note, it sounds like one of the first notes actually in the song. I'm going to check on that, and I'll let you know if I was right. Also, whoops, that was an accident. Also, post the song so you can see what I'm talking about. Okay, let's take a look at E. That's not E. That's 500 complex. Okay, let's get rid of that. No. This is 500 hertz, but we don't want that either. Here's E. Okay. So let me move over a little bit. Oh, this is the whole thing. Okay, so this is me saying E. This is what E sounds like. Well, it was actually very quiet. So sorry about that. But it sounds like E, just like that. So this is, again, our time domain. Let's zoom in a little bit. Now, what do you think is going on here? I'll tell you what I think. To me, it looks like that is not one replication of the same wave. And that looks like a half of a replication. And I say that because the amplitude of the wave on the left side, right here, is a lot higher than the amplitude of this wave. This wave looks about the same as this one, and then this one is a lot lower. So I think the wave is actually going from here to here. Now let's use our little trick again and look down here. The length is 0.008 seconds. That's the time it takes for one cycle of this wave to complete. So, oh no, I got rid of my calculator. Hang on. All right, so 1 divided by 0.008, 125. So it looks like my fundamental frequency might be 125. Let's see if Audacity agrees. First, let's do the pretty one. Let's look at the spectrogram. I'm going to shrink this channel so we can focus on just one. This is a dual channel recording because I did it with my microphone instead of generating the tone myself. And the channels should be identical because of that. So we can just look at one. All right, so we need to zoom in a little bit. So if you move your cursor over here, you get this magnifying glass. If you left click, it zooms in. If you right click, it zooms out. Let's zoom in one more time. Okay. So it looks like I might have been wrong. But 250 seems high. So the spectrogram is showing that most of the energy is centered around 250 hertz right here. This is the white hot band of energy here, and this is 250 hertz. I'm going to right click over here to zoom out. Although, you know what? Yeah, this right here, this looks like a second band of energy right around 125. And that makes sense. So we've got a 125 hertz fundamental frequency. When you zoom out, you can see it a little bit better. 125 hertz fundamental frequency, and then this 250 hertz harmonic that is actually more intense than the fundamental frequency. That's okay. That's not unheard of. In fact, that's what creates formants, if you've heard about formants in speech. Formants are harmonics that are accentuated more than other frequencies in the harmonic series. Okay, so let's highlight a portion of this. That's, it's probably too much, but whatever. We'll go to Analyze, Plot Spectrum, and see this is what real sounds actually look like. They're a little noisier than what I've been showing you. So there's harmonics that go all the way up. There's noise from my recording environment. There's artifacts from analyzing the sound. This is what real audio looks like. Okay. But good thing we still have this peak tool. So this says my peak frequency is about 115. And then there's a harmonic here at 252. There's another harmonic at 373. And there's another harmonic at 506. Now, does this track? Does that make sense? It seems to. It seems like this one might be a little mistuned. But 115, if that really is our fundamental frequency, the next one up would be 130. Nope, sorry, 230. 230 is not too far from 252. And then 373, we should be at 345. And then moving up again, we should be at 460. So here we're 40 hertz off. Now, if this is right, if our second harmonic is right, 252, or about 250, this should be 125. This should be 375, which is very close. This should be 500, which is very close. So it seems like this 115 is slightly mistuned. What if we bump our window up? That's a little bit better. Now it changes it to 129. Changes this to 254, 380, and 507. That's much closer to 125, 250, 375, and 500. So what you want to do is push your window out to the size that you can possibly get. Well, that's actually not good advice, because sometimes you get weird little artifacts like this. And I'll show you what these are. So this is probably 60 hertz right here. I mean, it shows up as 50 hertz, but it's likely actually 60 hertz. And what that is line noise from electronic equipment. It's pretty quiet, but it always travels at 60 hertz. And you pick this up on a lot of recordings. So you get these weird artifacts of the room, artifacts of your recording equipment, artifacts of me having multiple computers in here when I'm recording.
So we don't want to get that kind of stuff. 2048 is much better.
All right. So 2048 is a good one to go with. 1024, if you have a shorter sample.
Anything below that, here's what you get. It doesn't really make a whole lot of sense. It says that our fundamental frequency is 247, and then the next harmonic is 2523. So that's garbage. 512 is similarly garbage. You don't want to go below 1024. If you have a long enough sample to go to 2048, then you should.
Okay. So let's close that. Everything is in pretty close agreement, right? Our computation gives us exactly 125. Looking at the spectrogram shows us 125 and 250 as a second harmonic. And the frequency domain graph shows us close to 125. 115 if we use 1024, and much closer, 129 if we use 2048. So that's Audacity, and that's what you're going to be doing. I'm going to give you some speech sounds, and you are going to answer some questions based on those. All right, that's it for Audacity, but if you want to learn Praat, that's what's coming up next. All right, so if you want to use Praat, move around my noisy chair. This is what Praat looks like when you start it up. You're going to want to go to Open, Read from File, and then you just choose your file like normal. And here we go. Let's look first at 500 hertz. Well, actually, what's cool with Praat, not Pratt, in my home life, I call it Praat. I know it's not the right way to pronounce it, but I do. So what's cool with Praat is you can actually select multiple files to open at once. So here we can select all three of these and open them. You can actually do that with Audacity, but it opens three separate Audacity programs. So it's not quite as efficient, I guess. Okay, so here we've got our three sounds. So first, let's look at 500 hertz. We can draw it. When you click draw, it brings up this little box. And it wants to know the time, 0 to, and then if you put in 0, it means all of it. And the amplitude range 0 to, and then again, if it's 0, that's auto. So these are just the defaults, and you can leave it there. Okay, well.
So that's our 500 hertz tone.
It's a little too much for us to actually see what's going on. Let's, I'm going to make another. So to draw in Praat, and when I say draw, I actually mean have it draw something. you can you have to make this box around where you're having it draw. So that's one difference between Praat and Audacity. So we're going to go back to draw. We're going to draw. And for my time range, I'm actually going to give it 0 to, let's just look at 3 cycles. So 0.006. Okay, there we go. All right, so we've got 1 cycle, 2 cycle, 3 cycle. Great. Our marks here, we've only got 0.006, so if you were going to compute it the way that we did in Audacity, you would have to take 0.006, you'd have to take 3 cycles in 0.006, you'd have to divide 0.006 by 3 to get 0.002, and then you could figure out the frequency from there. But that's okay, we already know that it's 500. So let's take a look at the next thing. All right, so we want to click on 500 hertz and go over to Analyze Spectrum and then to Spectrum. That brings up this little box over here. You can always just click OK on this. You can either do it fast or not. Fast is fine. Click OK. And that creates this new sound file called Spectrum 500 Hertz. So let's do one other thing before we start drawing things. Go back to Sound 500 Hertz. Go to Analyze Spectrum again, and then go to Spectrogram. Click on that. That brings up this dialog box. And this is all fine. Go with your defaults on this. Click OK. And now you have Spectrogram 500 Hertz. So you can go over here and clear everything in your picture window. The way that you do that is go to Edit, Erase All, and then you just click and drag where you want this to be drawn. So I'm going to go that much, and I'm going to go to Spectrum 500 Hertz. I'm going to click on Draw. Let's do the log frequency. No, let's do the typical. We'll go to Draw. That brings up this dialog box. This is, let's change the frequency range so we can get a better view of it. Because if we don't change it, it's going to go from 0 to over 20,000 hertz. And the human range of hearing is 20 hertz to 20,000 hertz. So there's no reason to go over 20,000. Not if we're just looking at what we are hearing. So we know that this is 500 hertz. Let's just go to 5,000. And we'll click OK. And there we go. Now, before we talk about what that picture looks like, I want to draw another picture. So go ahead and move your area of drawing down a little bit. Click on Spectrogram 500 hertz. Draw. Click on Paint. Brings up this dialog box here. This is all fine. Well, actually, let's cut our frequency range again down to 5,000. And yeah, that's fine. All right, so then we'll click OK. And there's a spectrogram. All right. So let's look right here. What do we have? Well, it's a frequency and amplitude plot, right? So we're looking at frequency domain. This is just showing us that we've got this spike at 500 hertz. Now, how do we know it's at 500 hertz? Well, it's hard to actually figure that out. We got to play around with our axes a little bit here. And we can do that. Let's get rid of this. We erase all. We'll go back to spectrogram. We'll go back to draw. This time let's draw the log frequency just to see what it looks like. Okay, the log frequency actually gives us better axes, labels here. So again, this is amplitude on your y-axis. On your x-axis, we've got frequency. And here you can see that the spike is at 500 hertz. That's great. Let's make, well, that's a little too big. There we go. So let's erase that again. Let's take a look at the spectrogram again. Draw, paint, gives us this dialog box. This all looks fine still. So we'll click apply. And our axes are still weird. So if we go to Spectrum 500 and we click on View, you get this window, and we can actually we can zoom in, and I've zoomed the wrong way. We can set our range too. There, that's what I want to do. We want to go to zoom, not set range. So zoom, we want to look from 0 to 5,000. We'll say okay. Aha, there we go. There's the spectrum that we saw earlier. So now you can click near where this peak is, about on it there. We've got 494 about is where the center of this peak is. 484. It's not quite on it. You know, 493 is what it looks like. So that's actually pretty close to the estimate that we got from Audacity. Not quite 500, but very close. Okay, so we can get rid of that. And then if we want to look at the spectrogram, we can do the same thing. Just view it. Here's the spectrogram. And this is showing us, you can see that there's not any energy between 1,000 and 5,000. There is a band of energy below 1,000, and it seems to be centered about halfway between 0 and 1,000, so right around 500. The resolution on this color isn't quite as good as Audacity, but it, you know, it serves the same basic function. Okay, so now another thing that's really cool about Audacity is you can do these things for multiple sounds at a time. So if I select 500 complex and then I hold down Control and I click on E, sound E, I can click on Analyze Spectrum and go to Spectrum for both of them. Here's the box that pops up. Why are you not moving? There we go. Here's the box pops up. You click OK, and then we have the spectrum for both of those. We can do it again. Go to Spectrum. Go to spectrogram. This dialog pops up. It's fine. And now we have Spectrum and Spectrogram for both of our other files. So we're going to want to click on 500 complex. We want to view. And look at that. We've got 3 peaks. So this one's around 475. That seems a little too low. This one is, let's see, I'm not right on there. 1,013 roughly. And that one is 1461. So we're close again. 500, 1,000, and 1,500. Audacity might have been a little bit closer. I think that's mostly because the cursor will just snap to the point where the maximal amplitude is. But this is close. You could make an educated guess about what the actual fundamental frequency is here. And actually, we can zoom and get a little bit closer to this action and be a little bit more sure as well. Let's say we only want to go to 3,000 hertz. All right, there's more peaks, and you can see that we were off now that we're closer. So 491 looks to be about that estimate. 1,003, which is exactly what we found in Audacity, and about 1,490. So we're a lot closer once we've zoomed in. That makes sense. We didn't do it in a log plot, so you can see that the spacing between 0 and 500, between 500 and 1,000, between 1,000 and 1,500 are all very equal. And that's what we like to see. Okay, so let's get rid of that. Let's look at the spectrogram for 500. We want to view. And this looks a little different too. Now we've got 3 bands of energy. One is centered right around 1,000. One is down here at approximately 500. And one is up here at approximately 1,500. And that's what we like to see. We can tell that there's 3 bands because there are areas of white separating them, so less intense right here and right here. So we know that there's 3 bands of dark black, which means these are the ones that are in the sound you're listening to. All right, we'll get rid of that. Now let's look at the spectrum for E. We're going to click on that and view it. That's going to bring up this box. We want to zoom. And, you know, let's just go up to 3,000 on this one as well. All right. So we've got a few harmonics here. This one seems to be, about 125, pretty much right on the money. There's these few little transient sounds down here, but they're kind of low in amplitude, so they are likely, again, like I said last time, just line noise from the electrical equipment that's in my office while I'm recording this. But you can tell the fundamental is pretty powerful here, and the line noise is not. So 125 for our fundamental frequency. Our F2 is 247. It should be 250. That's really close. Very good. And third harmonic, 375, right on the money. Fourth harmonic, about 503. It should be 500. So it's very close. This is great. So that's E. Let's take a look at the spectrogram for E. We want to view it. And here's the spectrogram. There's a lot of information between 2,000 and 4,000, but it's not very clear. There's not a lot we can resolve there. So, doop, doop, doop. So you can see that the spectrogram for Praat is maybe not the most clear. 1,000 hertz is here. This is a little bit lower than 500 hertz. I mean, we know that it's probably showing up at 250, and the fundamental is a little bit below it at 125. This seems to be showing 250, though it's quite a bit below. Well, sorry, it's not quite a bit below. It's not very clear. It's just not very clear where that frequency actually is. So the spectrogram on Praat leaves a little to be desired. But in any case, that was Praat. That's how you look at
everything in Praat. Everything that we've already learned about in Praat.